So, a principal submatrix for a given matrix is nothing but leaving the you take a set of k entries. Suppose I am looking at a k by k submatrix. Okay. So, a principal submatrix is nothing but you look at the k rows and the corresponding k columns of the matrix and you pull out that submatrix, then it is called as a principal submatrix. So, in general any submatrix is nothing but I have a set, say S and T, say S and T are numbers, they are subsets of 1 to n, the labels of our matrix. Okay. So, if it is an n by n matrix, so we say that a submatrix AST to be nothing but the elements which are having the row entries coming from S and column entries coming from T. Okay. Say suppose I have S to be equal to 2, 3, 4 and T is say 1, 2, 7, some entries like this, and so I should obviously have my matrix A to be an order of at least 7, right, because I have given a row entry 7, column entry 7. So, let us take it as a 7 by 7 matrix. So, a submatrix for AST is going to be here, it is nothing but all those entries where entries of the form A21, A22, A27, A31, A32, A37 and A41, A42, A47. So, this is a submatrix. Given any matrix, you can construct submatrices like this. So, from here, if I want to focus on principal submatrices, principal submatrix is nothing but my S and T are the same set. Okay, I should have my same, I am like looking at the rows and columns coming from the same set of values. Okay. So, if suppose I want to say a principal submatrix of order like 3, 3, so what will I do? And I have not said what 3 entries that I am going to look at, say 2, 3 and 2, 3 in set form. So, this would be nothing but A22, A23, A32, A33, right. So, this is going to be the principal submatrix of order 2 by 2. So, like this you can look at all the principal submatrices, and a minor is nothing but, so we have talked about principal submatrix. So, to officially define it or formally mathematically define it, a k by k submatrix, I should say a submatrix of A which is formed by taking k rows and the same k columns or corresponding k columns. If I take 1, 2, 3, then I take 1, 2, 3 columns, right, and the corresponding k columns. So, now a minor or a principal minor, a minor is nothing but determinant of a submatrix, and a principal minor is a determinant of the principal submatrix. Okay. So, now if I want to translate this into our eigenvalue definition, how should I be writing this in terms of minus? So, let me go back. So, now I have this representation. In this representation, I am trying to connect the minus actually. Okay. So, that is how we can look at the entries and the eigenvalues, the behavior of them. So, if you look at this, every lambda i's have like the coefficient of every lambda power k term, if you look at it, this is nothing but obtained from the determinant of the principal subminus of that order. Okay. Say for example, the last term lambda n this term lambda 1 to lambda n. What can we say about this? Or is it like it's the determinant that we have already said? Okay, then let me go into this part. The first one, lambda 1 plus lambda 2 and so on, lambda n. That's trace of A. In another language, it is also nothing but if you look at all the 1 by 1 submatrix, principal submatrices, okay, it is nothing but sum of all the determinant of principal submatrices. So, what is the determinant of 1 by 1 principal submatrix? So, determinant also has a new definition using principal minus, as this would be nothing but A if your order is equal to 1, right. If you have just one entry A11 alone exists, so determinant is going to be A11 or the matrix A itself, right. Or it is also going to be, this is the standard definition that you have read in terms of how you define, like in your school days you would have started finding determinant. Take the first entry, leave out the first row, first column and look at the submatrix of that whole thing, right. So, the same way here we can write it as minus 1 power I plus j, aijth entry, right. You look at the aijth entry and multiply it with the aij minor. Okay. So, when I write this aij in this form, I am not calling it as a principal submatrix form, but I write it in this way because just to say that I am leaving the ith row and jth column. Okay. So, this notation is the other way around of my minor what we are talking about there, right, just for notation sake. So, this is the usual definition that you have seen where j runs from 1 to n. You can fix any row, you start from any row, you do this, you get the determinant, right. So, the I here is kind of fixed, you take any one ith row, right, and over j as you vary you will get the determinant. This is the standard definition that you have seen, right. So, now coming back to our principal, this aij would be also nothing but the submatrix that we are talking about, and the corresponding aij would be, we will look into the determinant of aij, right. So, this is another definition, an alternative definition for the determinant of a matrix, right. Excuse me. Okay, so where were we talking about? I came from principal minus. So, this in similar language, if you say, there is also another definition. If you look at 1 to n we have, if you expand this, what do we get? If you expand this whole formula, you get every term has, it is like a CNF, okay, what you have already seen. Every vertex will have n terms, right. You will have A11 into A12 into A13 and so on. If you expand it, it is nothing but summation over terms of this form. You have a permutation of the 1 to n matrix. If you have a permutation, say suppose I look at 1 to n and I consider a permutation of this. Okay, so how many permutations are possible? N factorial permutations are there. So, the summation is going to run over all possible permutations. So, you will look at A1 sigma 1, A2 sigma of 2 and so on, An sigma n, and the summation runs over all sigma over all permutations of 1 to n. Okay. Or in simple terms, mathematically if I want to write, I will just write it as Sn, set of all permutations coming from 1 to n elements, right. So, before this there are certain things I have left the gap. What will it be? Is it, if you look at this A1 sigma 1, A2 sigma 2, everything is positive entity, right. At least I do not know if whatever is the elements are, but your determinant always has an alternating sign, right. So, there is another term here which contains sign of sigma. So, every permutation has a sign associated with it, whether it is positive or negative, like SGN is going to be defined as plus 1 or minus 1 depending on my sigma is even or sigma is odd. So, going back, for mathematics students it would be easy to look at what is an even permutation or an odd permutation. So, what is an even permutation? Okay. So, given a permutation, if you can write it as product of even number of transpositions, right. Say for example, suppose I have say 1, 2, 3, okay, and I have this cycle, okay. So, what is this? 1 goes to 3, right, and 3 goes to 2, 2 goes to 1. So, this is a cycle, we usually write it as 3, 1, 2. Right, that is 1 goes to 3, 3 goes to 1 and 1 goes to 2, right. So, did I write it correctly? No, I am sorry. 1 goes to 3, 3 goes to 2 and 2 goes to 1, yeah, I am sorry about that. So, given any cycle, right, we can write every cycle as product of transpositions. So, what is transposition? It is just 2 element permutation. You only transpose 2 elements, you fix all the other n minus 2 elements, right, that is a transposition. So, every cycle or every permutation can be written as product of cycles and transpositions. This is a very standard theorem you would have studied in basic algebra. So, now here this element, it is nothing but product of the transpositions 1 2 and 1 3. Okay. So, I give this as an exercise for you people just to verify that the left side transpositions will give you the the right side product of transpositions give you the left side permutation. So, you know how to multiply to compose 2 permutations, right? I think that part is clear. So, what is the first permutation? I have 1 2 3, we have 1 2, that means what? 1 goes to 2, 2 goes to 1 and 3 is fixed, right? This is a permutation, and the second one is 2 is fixed and this is what we have. So, if I just multiply these two, what do I get? 1 goes to 3, actually here composition goes, when we do a composition we take from left and then going to right. So, 1 goes to 3 from the right side, you have 1 goes to 3 and 3 goes to 3 again, right, and 2 goes to 2, 2 goes to 1, 3 goes to 1 and 1 goes to 2. So, you can now verify that the cycle which we started over here and the product of transpositions are same, right. So, now given this is a 3 element permutation, right. So, we can write this as product of two transpositions. So, this means what? This permutation is an even permutation, okay. So, with this understanding we can see now given any permutation of 1 to n, the summation over every permutation gives us with this product, right, a1 sigma 1, a2 sigma 2 with a sign of the permutation gives you the determinant of the matrix A, right. So, now this again if you go back here, it connects to this entity is nothing but it connects to your sum of all principal minus. So, as we go back you can just see that this entry here, the lambda 1 to lambda n, lambda 1 plus lambda 2 plus lambda n can be thought of as the product of 1 by 1 determinant of 1 by 1 principal minus and sum over every element, right. And similarly lambda power n minus 2 will be nothing but sum of all 2 by 2 principal minus. Okay. And so on, we can see that at the last you have to look at every entry. So, the last one would be nothing but determinant of the whole matrix itself. So, is it clear now whatever we are doing now? So, with this understanding I just want to go into the eigenvalues of our graphs. So, what can we say about a matrix A and its powers? Say A square. Okay, A square is nothing but P inverse D square P. This is what you want to say, right? Okay, but before this what can we say about, even for A I could have done the same thing, right? I can still write my A as PAP inverse or PAP transpose in this case, right? No, that is not my question. I am coming to my question again connecting to graph theory. Okay. So, what does a matrix A square represent? for a given graph. We know A is the adjacency matrix, right? What about A square? Okay, so we have two edges between. Okay, so how do you translate that in terms of graphs? Parallel edges. You are somewhere nearby, but still you are not telling me what two edges, where should the two edges be? Okay, let us do a simple exercise. Take this matrix, take this graph. So the corresponding matrix A is going to be, of course I have taken a 4 by 4, so we have 0 1 0 1. So what is A square of this matrix? You can multiply that, right? Yes, who is going to fill me this quickly? First row, anybody? How many numbers I am hearing for a matrix multiplication? Is this okay, or I haven't completed it? Who is going to complete it for me? So it should be symmetric, right? So is everyone convinced about this? At least have I done it correctly? You can cross check it. Okay, now if we look at these entries, how can you connect them with the graph? Actually, I did not multiply the matrix, I took it from the graph and I wrote the entries. So now I am asking you the reverse question. So any entry Aij, in any entry here, it just represents the number of paths or walks, I should not say path, number of walks of length 2 from I to j. Okay. How many number of walks are there? So A square represents the number of walks of length 2 from I to j, that is present. So the diagonal entries, if you see, it is going to be equal to the degree of every vertex, because from that vertex I can go to the neighbor, come back, right. So it is a walk of length 2 always. So there are n possibilities will be there for every vertex. So diagonal entries would be nothing but the degree of the matrix, degree of the graph, okay, and every off diagonal entries will give you the number of walks of length 2. Okay. This also generalizes to any k. Okay. So if I want to talk about a power k. Okay. So this is nothing but, I will just write it as aij with a bracket, no, k in top. So this is going to be nothing but number of walks of length k from I to j. So, why are we doing this? To connect our matrices. Again, we will go back to the matrix theory here. Okay. So, if you look at any two given vertices I and j, okay, what can I say about the corresponding matrices, say a square, a cube and so on? Do they have any connection between them? Okay, or I will put it in the other way around, I will bring in the notion that I am looking at. Suppose my two vertices I and j are at a distance, say m, okay, dij is equal to m. Then what can I say about the matrix up to power m, like a square, a cube and so on until a power m? Can these two vertices I and j in the graph, can they have a walk of length say 2 if they are at distance at if their distance is m? So, maybe here I will just improve on it, say suppose I add a vertex 5, I should add something more I guess. Say vertex 6 is at distance 3 from my vertex 4, right. Yeah, it is a distance 2, okay, it is again centrally situated. Okay. So, what can I say about its entry in the previous powers of A? Okay, let us modify this graph. Say I talk about the vertex 1 and 6, start with 1 and 6, we know the distance between 1 and 6 is at distance 3, right, they are at distance 3. What can we say about the A square, the entry of 1 comma 6 in the A square matrix? 0, right. So, their shortest path distance is minimum is like 3 now. So, if you look at all the powers of the matrix A, okay, that particular entry will be 0 till the distance m, because that is the first place where they are going to even walk if you are talking about. So, first minimum distance should be touched, after that it may have entries, right. So, in this sense we can say that if I and j are two vertices at distance say m, then the corresponding matrices I, in fact we can also include identity matrix here. So, I a square until a power m, okay. All these matrices are linearly independent, okay. So, we know what is linearly independent, right, you cannot write one as a linear combination of the remaining entries, right. So, the same definition we will just extend it for matrix also. So, then all these are linearly independent. So, one simple reason is we know it is because the distance is m, obviously all the entries of a square up to a power m minus 1, they will all be equal to 0, right. And similarly, if you see the corresponding entries which are at distance before it will also get altered, say like 1 and 5 if they are at distance 2, right. So, until a square it will be having 0, right. So, all these kind of things will compose together, and we can give a formal proof for this. This is actually a theorem which I did not want to write, but which says that in a graph, okay, of course we are in undirected graph, given a graph G and two vertices at distance m, then the matrices I, a square, a power m are all linearly independent. So, what is the corollary for this? If I say this, then I should be able to talk about a corollary also attached with this. So, we have to again connect to our eigenvalues, right. So, when I say they are linearly independent, then I can see that the rank of the matrix is at least m when two vertices are at distance m and I have all these powers are linearly independent. So, this also leads to the fact that the matrix M, the matrix A has rank at least m, okay, and so the largest eigenvalue or the eigenvalues, we know we have already seen the sum of the eigenvalues is trace. In similar direction, we can say that the largest eigenvalue is going to be less than or equal to or greater than or equal to d, the diameter of the graph. I give that as a question, think over it. So, what is the connection between the eigenvalues? In fact, largest eigenvalue is what I am bothered about, lambda and diameter of the graph. Or in fact, okay, even if this is going to be very difficult to see, let me just rephrase it. We will get back to this a little later. So, if you look at the number of distinct eigenvalues, that you can now connect immediately, right. So, if k is the number of distinct eigenvalues, because I have said already rank is going to be m. So, there are at least m distinct eigenvalues, right. So, the same way if we talk about diameter, then I can say that the number of distinct eigenvalues is going to be strictly greater than the diameter. No, here I will just modify this, I will get back to this because it is little difficult to see at this point of time. So, we will get back to this, and already I have said lambda 1 is the largest eigenvalue, positive, right. So, we will remove this now, we will get back a little later, we can connect the diameter and the eigenvalues, we will go to that. So, at least from the previous discussion, what we can conclude is, since I know that there are m plus 1 entities here like I, a square, a power m, they are all linearly independent, I should be able to see that there are at least d distinct eigenvalues present. Okay. In fact, it is greater than d, okay. I said k strictly greater than the diameter. So, now coming back to the first question, then let me just quickly revamp and we will continue in the next class. Okay. So, we are still left to answer where we started with Kn, right. I went from here to matrix theory. So, we have to still answer the question of spectrum of complete graph, and we will do all these things later. So, is it clear or any doubts? So, think over it, you give me the answer what will be the eigenvalue for Jn and hence the complete graph Kn.